Deep inside our devices, microscopic transistors process digital information at a nanoscale, orchestrating our modern world with flawless mathematical precision. But that delicate math collides with a brutal reality at the power plant. Heavy generators pump out alternating current, a massive, untamed wave of electricity. This animated diagram shows exactly why these two worlds don't mix. Alternating current violently reverses direction. If you feed those undulating waves into sensitive microchips, the constant reversals will instantly burst capacitors and fry delicate logic boards. Before automated digital systems could actually perform useful work in the physical world, engineers had to figure out how to tame those high-voltage waves into strict, predictable lines of power. The earliest attempts to force alternating current into steady, direct current were entirely mechanical. Engineers relied on massive, roaring rotary converters, literally using electricity to spin a giant motor just so it could physically crank a separate generator. The first real step away from physical motors came from Peter Cooper Hewitt. In 1901, he developed the Mercury arc rectifier, a glass bulb filled with mercury vapor that passively stripped away the negative half of the AC wave, creating a one-way street for power. This evolved into the diagram we see here, the Thyratron tube. By placing a control grid between the electrical contacts, operators could send a tiny voltage to ionize the internal gas. This caused an avalanche of electrons to flow through, locking the circuit open. This latching behavior meant you didn't have to keep expending energy to hold the gate open. The Thyratron worked well enough for heavy industry and early radar, but wrapping high-voltage arcs in fragile, gas-filled glass tubes was dangerous and wasted immense amounts of power. The electrical grid needed a rugged, solid-state replacement. The solution wouldn't come from heavy power engineers. It came from scientists working on low-voltage telephone signals at Bell Labs. In the late 1940s, researchers like John Bardeen, Walter Brayton, and William Shockley invented the point contact transistor. It was a tiny, solid-state device built out of germanium, designed solely to take a weak audio signal and amplify it. While trying to test the resistance of these early transistors, the engineering team zapped them with heating pulses from a capacitor. The result was bizarre. The transistors suddenly outputted an inexplicably huge surge of current, far more amplification than the physics predicted. This diagram illustrates what William Shockley realized. The intense heat from those pulses had actually altered the atomic properties of the germanium. It repelled the positive electron holes and attracted negative electrons, forming an inversion layer. The heat had accidentally mutated a 3-layer PNP transistor into a distinct 4-layer stack, PNPN. Using the structure, Bell Labs scientists Joule Ebers and John Maul proved that under the right conditions, those internal layers would egg each other on in a positive feedback loop. The two halves of the switch would trigger each other simultaneously, locking the solid rock into a permanent glowing on state. By pure accident, a team trying to improve microscopic logic switches had reverse-engineered the exact latching mechanics of a heavy-duty power tube entirely inside a block of solid semiconductor material. Fascinated by this 4-layer anomaly, Shockley left Bell Labs to build it himself. He set up shop in California, intent on turning the PNPN structure into a 2-terminal diode for the massive telephone switching market. But producing these complex raw silicon components in the late 1950s was incredibly difficult. The manufacturing processes were inconsistent, resulting in severe thermal leaks. Once activated, the diodes would often overheat and refuse to turn off. Telephone companies quickly found the Shockley diode practically useless because it lacked a reliable way to trigger that breakdown. Frustrated by his rigid management and the unworkable product, his top staff walked out to form Fairchild Semiconductor. Shockley's 4-layer silicon sandwich worked perfectly on paper, but it was useless in reality. It sat stranded as an elegant mechanism without a market, waiting for a completely different set of engineers to find it. Gutzwiller was leading a team at General Electric tasked with rating germanium-based rectifiers. He was convinced that the power industry needed a silicon-based equivalent to the Thyratron tube, one capable of surviving the intense thermal and electrical stress of high-voltage grids. When Gutzwiller's team read the Bell Labs paper on the PNPN structure, they recognized a familiar behavior. The mathematical model for that latching logic gate perfectly matched the requirements of a high-power rectifier. In this diagram, we see GE's vital modification. They took the existing 4 layers of silicon and simply added a third physical terminal to the middle, a gate. By sending a small pulse down that wire, the operator could instantly force the circuit to break down and let current through on command. Armed with the first working prototype of this silicon-controlled rectifier, Gutzwiller went to a local hardware store and bought an electric hand drill. He wired the silicon to the motor, slowly turned the control dial, and watched the drill spin up to full speed without exploding. By taking a microscopic telecom design and engineering it for raw voltage, General Electric successfully created the world's first solid-state motor control. The industry scrambled to adopt the technology. This rugged sliver of silicon rapidly replaced the fragile glass power tubes, eventually earning a portmanteau of the words Thyratron and transistor, the thyristor. Here we see the true power of the thyristor. Because it switches so incredibly fast, engineers can practically slice a raw power wave into highly specific segments. This allows us to smoothly dim an LED bulb or precisely throttle an electric car motor. Today, advanced descendants of this very technology manage continent-spanning high-voltage lines, efficiently routing gigawatts of power to massive modern cities. The silicon transistor receives all the historical acclaim as the brain of the digital age, but without the thyristor providing the solid-state muscle, we'd have no way to power it.